So we'll just start with grade class at this point. Okay, so we're going to do what we always do, which is we're going to take a slab of this water, and we're going to figure out what the work would be to take that random slab and bring it up to the top of the tank. And then we'll add it up for all the slabs. Okay, so really it's the same concept as we've been using all along. Okay. So I'm going to assume that this slab has a thickness of delta y, and that it's located at some depth y. And I'm going to let y be equal to 0 up at the surface, and then plus y goes down. So the volume of my slab, what shape is the slab? What? It's a rectangle. Yeah, it's a rectangular solid, okay? Because what are my dimensions here? So this dimension is 12 feet. This dimension is 10 feet, and the whole height of the tank is 20 feet. So how do I find the volume of a rectangular solid? How do you find the volume of what? Go ahead, Fiona.
The base and height.
Okay. So length times base, length times width times height. Okay. So length times width times height. So that's going to give me 10 feet times 12 feet, but the height is going to be delta y, which is how I'm kind of going to get these little values in here. Okay. Now we've been told that when we're dealing with lifting things, that the force that it takes to lift it is equal to the weight of that object, right? Okay, I mean, that's what we were told, okay? So this F up here is going to be the weight. So that force is going to be the volume times this weight density, which is kind of like regular density, but instead of being mass per volume, it's weight per volume. And that's that number that we're given in the beginning, that 62.4 pounds per cubic foot. Okay, remember that pounds is a unit of force. So my force here is going to be this 120 times delta y times 62.4. And what do we get for our force then? Somebody could multiply that out first. 120 times 62.4. Agni, what do you got?
7,488.
Okay, so 7,488 times delta y. Okay. So we said at the very top that work is equal to the force times the distance in some way. Okay. So I've got my force now, and the distance is going to be y. And the distance for each slab is going to be different. Okay, because I let y be equal to 0 at the top of the tank at the ground level. So if this is my slab here, it's got to go up y in order to be pumped out of the tank. Oops, go away. Okay, so my work is going to be equal to, it's going to be an integral because my y's are going to change. And I have to add it up for each of the different individual little y's. And when I add up a whole bunch of individual little y's, I get an integral. Okay? So that's going to be my force, which is 7,488. I'm going to turn that delta y into a dy. So that's my force. And then the distance I'm moving it is y. I did end up recording the class just because so many people had felt it necessary to leave the room, not really not casting aspersions. I'm just saying that it's there if you need to go back and catch up on what you missed. Okay. And then, of course, I'm going to have limits of integration. So what are those going to be? Dagny. Right. So I would say 0 to 20. Okay, but yeah, the piece that's all the way at the bottom, the slab of water that's all the way at the bottom is going to have to go up 20 feet. The slab that's already near the top is only going to have to go 0 feet. Okay. So I've come to an integral. What's the first thing I ask myself? Can I do it by inspection? Can I? Yeah, okay. What's the antiderivative of y going to be? Y squared divided by 2. So that's going to give me y squared over 2 times 7,488. And I'm going to evaluate that from 0 to 20. I did end up recording this class, so if anybody needs to catch up on the parts that they missed, that will be there. And then what do we end up with here? It's a really big number, if that gives you permission to share your answer. Katie, what do you got?
1,497,600.
What other people got? Give or take? Okay. And remember that our stupid units for work in the British system are foot-pounds. Okay, everybody understand how we got where we were going? Okay. So part B says, if the water is pumped to ground level with a 511 horsepower motor, work output 250 foot-pounds per second, how long will it take to empty the fuel tank to the nearest minute? Okay, so let's unpack that a little bit. So we have this motor, and the motor is going to literally do work. Okay, it's what a motor does. And it's 250 foot-pounds per second. So what is foot-pound a unit of again? Work, okay. And work has the same units as what other quantity, my AP Physics people? What? energy, okay? So this is really energy per second. And what do we call energy per second? My AP Physics people. Well, all right, what is the AP Physics unit for energy? Joules. So what's a joule per second? Power. And what's the unit we usually use for power? Watt. Okay, what comes in watts? Where do you see watts in your life? Katie?
Light.
Light bulbs. Okay, so usually you have like a 60-watt light bulb. Or now if you have energy efficient light bulbs, they're like 42-watt light bulbs. And that means that they give off 42 joules of energy every second. Okay, so this motor is going to produce 250 foot-pounds of energy every second. Okay, so this is power or energy per time. And do I know how much energy I need altogether? How much energy do I need altogether, Fiona? You nodded your head, that's why I called on you. I didn't mean to randomly call on you. How much, help her out, how much energy do I need altogether? Yeah, it's the answer to part A. It's the one, we could even put it in scientific notation, it's the 1.4976 times 10 to the 6 foot-pounds. Okay, so I know how much energy I need to produce. And I know that every second my motor produces 250. So how many seconds do I have to run my motor? Okay, so 5,990.4 seconds. I don't know how many. I have no idea what that means. Let's put it into a unit that is something we can like relate to. Okay, so, sorry, excuse me. Can we convert that to minutes? How many minutes is that? Okay, so let's just call it 100. Because it was 99.84. So it's about 100 minutes, especially if we start considering significant figures. Okay, so we'd have to run it for about 100 minutes, just shy of 2 hours. Okay, we good? Kind of making sense? My Zoom friends, you doing all right? Okay. All right, so the last part says, show that the pump in part B will lower the water level 10 feet, halfway, during the first 25 minutes of pumping. So how do you think we're going to do that?
of, no, and then,
Okay, let's start with the first part of your idea. Okay, so if we know how many minutes our pump is going to run, then we know how much what we're going to deliver. Well, no, the power is the rate. If I know the amount of time, I know what am I going to deliver? What's the pump going to deliver? What? What are the units of power? Or power is what per what? What? Joules per second. So in words, if we separate it from units, what does that mean? It's what is joules measure? So it's energy per time. And if I multiply that by the amount of time I'm going to run it, what do I end up with? The energy. Okay, so I'm going to have the energy that I'm going to deliver. And my AP Physics people, what is work, really? It's a transfer of energy. So if I know how much energy my pump is going to give me, then I know how much work is going to be done, right? Okay, so let's start with, you all tell me, if I run my pump for 25 minutes, how much energy am I going to generate? Lily, I'm going to call on you, just so you know. What'd you get? Okay, so 375,000, and it's a measure of energy, so it's a foot-pound. Okay, is that what other people got? So now's where it gets a little tricky, okay? Because what I want to do is know what that height is gonna, how that height is gonna work into it, okay? So I want to back up for a minute to here, okay? Because that's how much work is done emptying the whole tank. And I want to figure out what depth I go to, what height I go to in 25 minutes. So I'm going to take that formula and I'm going to say that the work is equal to 7488 divided by 2, whatever that is. Okay. Times y squared. But if what I want to know is what depth it's emptied to, I'm going to evaluate it. I'm going to change my limits of integration and evaluate it from 0 to d. And I'm going to say that that's equal to 375,000 foot-pounds. Okay. Then I can sub in, so I think 7488 is 3744. D squared minus 0 is equal to 375,000, and then you can solve for D. So what's D going to be equal to? Dagny, what you got?
10.
Okay, let's see. What did other people get? 10? Okay, and that's exactly what they asked us to find or to show. Okay, questions on this? Dagny.
So if you were going to do it the other way and that you were like proving the time,
Okay.
would you just take the power equals work over time equation and plug in work done from 0 to 10?
Yeah.
And then find the time that way?
Yeah. So Dagny wants to know if we instead wanted to find the time that it took to empty the tank in half, then what we would do is start with this, but we would let D be equal to 10. We'd end up with an amount of work or an amount of energy, and then basically we'd go back and do part B again, where we looked at how much time it would take to generate enough energy to do that. Okay, any other questions? Right, it is on my list for this morning to finish the 6.4, 6.5 homework. I just didn't get a chance to do it over the weekend. Okay. All right, so one more problem. Okay, so that must be example 4. And so this one has to do with pressure. Okay. And one of the things that it has to do with is fluid pressure. And we're told that fluid pressure is W times H. And we'll talk about what those two things mean. So W is the weight density, which is what I called rho in the last problem. And basically it's just the weight per volume instead of the mass per volume. And then H is the depth. And so basically example 4 is going to talk about a fish tank. And that fluid pressure that pushes out on the sides of the tank come from this formula. And it kind of makes sense that the deeper you are, the greater the pressure would be, because there's a lot more water pushing down and therefore kind of pushing out. Because that water would like to be a nice flat puddle. Like that's what water does. Okay. All right. So a rectangular fish tank with base 2 by 4 feet and height 2 feet, those are the interior dimensions, so we don't have to worry about the thickness of the glass, is filled to within 2 inches of the top. A, find the fluid force against each end of the tank. Okay, so let's draw our tank here. Not perfect, but not horrible. Okay. So the length of our tank is 4 feet, 2 feet, 2 feet. But it's important to remember that it's not filled all the way up to the top. Okay, so there are 2 inches that are not filled at the top. Okay, we all got our picture? Okay, so let's take another walk down memory lane to freshman physics. I honestly don't know if you do this in freshman physics anymore. I always taught this in freshman physics. Do you do pressure in freshman physics?
We may have, but I have.
Okay. So pressure is force divided by area. So everybody stand up. Even the friends at home, stand up. Okay. So I know in fresh, yes, Amy, stand up. Thank you. Everybody up. Can you too? Okay. So she is standing up. Okay. So put both your feet on the floor evenly. Okay. So no like standing beside or anything. All right. And think about what the pressure on your feet feels like. Okay. Just be aware of it. And then don't lean on anything, but lift up one of your feet. And now think about how the pressure feels on the foot that's still on the ground. Okay. All right, you can sit down. You're not going to do this. I'm going to do it. But I have my stylus, right? And it's got a pokey end and a flat end, right? So if I push the pokey end in, it's going to hurt. It does hurt, okay? But if I apply the same force with the flat end, it doesn't hurt so much. What's the difference between the pokey end and the flat end? The surface area, the cross-sectional area, right? The pokey end, I'm taking that force and I'm concentrating it on a really small area, and it creates much more pressure. The flat end, I'm taking that same amount of force, but I'm spreading it out over a greater area, okay? So pressure is equal to force over area. So that tells me then that force is going to be pressure times area, right? If I go back and just cross multiply things. And I have another way up here to find the pressure, the fluid pressure. So I'm going to do what I do all the time so that eventually I can have an integral, okay? I'm going to consider a little slab of water that's going to have some thickness, delta y or dy. We can kind of stop kidding ourselves about the fact that we're going to change that delta y into a dy. And I'm going to find the fluid pressure against a small area at the end, and then we can add up all of the depths as an integral, okay? So this time I'm going to let y be equal to 0 at the bottom, and my slab is just going to be at some y. We're also going to assume that W is still 62.4, whatever it is, pounds per cubic foot. Okay, just like it was in the last problem. It's just kind of one of those standard things. Okay, we good? All right, I'm going to go to a new screen just to keep things from getting messy. So my pressure as a function of depth, P of y, is going to be that weight density, which is that 62.4 times whatever my y value is. Okay. And remember that F is equal to PA. So here's my P. I need my area. And that's the area of this thing right here. So what's the area of that little red band going to be? What? The area. Tia, you got an answer? 2 times dy. Okay. So this is going to give me 2 dy. And then I can say that the small amount of force, dF, that's on my little slab of water is going to be equal to P of y times the area, or 62.4 y times 2 dy. And if I integrate dF, I get f, and I get the integral of 124.8 y dy. And then what are my limits of integration? 0 to what?
I got 5 over 6.
5 over 6.
Now you have to convert
I'd have to convert what?
the unit.
To feet, right? But it's not 5/6 of a single foot. How tall is my tank? 2 feet, and it's to within 2 inches, right? So it's 1 5/6. Okay. Dagny, do you have that as a decimal for me?
Oh, I have it exactly. 11.
Yeah. This is math, though. I want
1.833.
what?
1.833.
Okay, so 1.833. I'm pretty sure those 3's go on forever. Okay, does everybody understand where that top number comes from? All right, if we go back here, remember, the water level doesn't go all the way up to the top of the tank. It goes up to y equals 1 foot and 10/12 of a foot, because it's 2 inches short, it's 2 inches away from reaching the top of the tank, okay? And then 10 divided by 12 is that 0.8333, okay? All right, so once again, you've come to an integral. Can you solve that in your sleep before your coffee? So tell me, what do I got? What'd you get, Tia? What? Okay,
It's like 209.
209.
0.733.
Oh, crumb. Hang on. Okay. Sorry, the video panel was doing that thing where if I touch it again, I'm going to lose it, and I hate that. Okay. 209 point what?
7.
We'll call it 7.
I used the repeating things.
Got it. We'll call it that. 209.7. Is that what other people got? Okay. And it is our usual stupid unit, foot-pounds.
Is foot-pounds like only in foot-pounds? When you're doing physical therapy, you've never seen foot-pounds.
We would never use it in physics because it would be stupid. I would imagine that there are engineers that use it, just because there are things that are left over before metric. But I would also imagine that we are probably the only country in the world that still uses it. And it's like sometimes I call it the British system. I have heard it referred to as the imperial system because it was the British system and the British Empire and all that. but I'm pretty sure the British Empire went over to metric. So it's really just us and our stupidity. And your calc book is written by, whichever calc book we're using is written by somebody who doesn't understand the connection between math and physics, because a physics professor would never use footpaths. It's stupid. It's just stupid. I can't tell you how, obviously you can tell how stupid I think it is. All right, so we good? Everybody understand where this is coming from? Okay? All right, so there's a part B to this. And in part B, I seal up my fish tank, and I take it and I turn it on its side so that I don't lose any water, okay? And now the base is 2 by 2, and the height is 4 feet. And how does the fluid force change on the rectangular sides? Okay. So, and I have written originally, what was the fluid force? Oh, on the rectangular sides. Okay, so we didn't really look at the rectangular sides, did we? We looked at the square side. Okay, so if we want to know how the fluid force on the rectangular side changes, we need to back up a little bit and make that change. Okay, so remember that the fluid force is the pressure times the area. Okay, and the pressure is going to stay the same, right? That's still going to be that 62.4 Y. But what's the area now if I'm talking about one of these sides here? What's the area of this side? Or more importantly, what's the area of this little slab here? Four dy. Yep, if all I'm talking about is my little slab here, that's going to be 4 dy. Okay. Okay. So we're going to do a little math hand waviness. There's actually nothing wrong with it. Okay. But remember that this is 2 times 62.4 y times 2 dy, right? All I did was pull out a 2. Why might I want to do that? What is this? Look in your notes. You're not going to get it by staring at it, or not your notes, but look in part A of the problem. What? Yeah, it was the force, right? So if I integrated it, I would get the force on a square side, but there's this factor of 2 out front. So I can say that the force originally on the rectangular side is 2 times the force that I found on the square side. Okay, I could go through and do the integral all over again, but sometimes you can take a shortcut. So that gives me 419.5 foot-pounds, okay? And that was for the situation in point A. And what I want to do is now in part B, remember I've taken my tank and I flipped it up. So it's sitting on the base, okay, on a square base of 2 by 2. So I've got a new tank, effectively, or at least I have a new situation. Okay, and now this is 2 feet, and this is 2 feet, and this is 4 feet, and somewhere in here is the water level. Don't know what that is yet, though. Okay, so I'm going to do the same thing again. I'm going to consider a slab of thickness or width delta y. I'm going to let y be equal to 0 at the top, and my slab be at some y. And I'm going to say everything that I said before, that df is equal to p of y times, actually, we'll call it dA, or at least the area of that little thing. So dF, it's still going to be 62.4 times y is going to be my pressure. And now the area on my side here is 2 dy. And I can integrate, right? So my integral of df is going to be f. I'm going to have the integral of 124.8 y dy. But the question is, what are my limits of integration? Why don't you try to figure that out? Katie, what do you think?
Would it be 3.82?
3 point what?
3.83.
Where'd you get that?
I did 4 minus the 2 inches. That would be.
Okay. So if I took this, which goes up to here, which is a certain distance from the top, and I turn it this way, does it, okay, now it's to here, does it go the same distance from this top as it did when I had it this way? No. So I've kind of changed the dimension, so I can't just say that it's still going to go within 2 inches of the top. So we got to think about it differently. Dagny, what do you think?
Well, if you find the volume of the original amount of water from part A, then you can find the amount of water that you need. So you can have your water be length number from part A to B. So part A would be 2 times 4 times 11 over 6 centimeters. And then you can find that, and you find the length and the width, and then you type in your variable.
Okay. We got what?
11 over 3.
Which is what in decimals? And then I'll repeat for my Zoom friends.
3.66.
Okay. So what Dagny did is she figured out the volume of water in the tank using part A. Okay. And they make it very clear when they talk about part B that we didn't lose any water. So Dagny got that whole volume for part A, and then she turned the tank. And she said, okay, so I know that the volume of water still has to be a rectangular solid, so it's still going to be length times width times height. And I know that the base is 2 feet by 2 feet. So she said, well, whatever the volume that I got from part A, which was equal to, let's see, I think I got 14.6664 feet cubed. So that was the answer from part A. That's going to be 2 times 2 times some, we'll call it H. Okay, where this is H. And then Dagny did the math, and she got 3.666. Okay? So everybody understand where that's coming from? Okay. All right, then what you can do is solve your integral and tell me what the fluid pressure is. Sorry, what the fluid force is. We got an answer? What do we got? What'd you get, Katie?
I got 838.
Okay, and again, that's foot pounds. So how does that compare, because that's really what this question asks, how does that compare to what the pressure was on a rectangular side when the tank was rectangular base down in part A? Yes, it's bigger. How much is it bigger by? Katie?
Approximately 4 times bigger.
I thought this was our answer. Because remember, it's on the rectangular side.
Oh, yes.
So that's what we're comparing this to. So what is it? Right, it's going to be twice as big. Okay, good. Got ourselves together here. Okay, so the other thing that we were going to do today was to start some review. So this is not the thing that we're going to read. This is your reading guide for tomorrow. It's here. So it should be, it's AP Exam Review 01. So start with problem number 1. And if you're done with number 1, go on to number 2. So what do you got? What's the answer to number 1? B. All right, who needs help on number 2? Do you remember how to do number 2? Maybe not? Okay. Let's look at number 2. So number 2 says we've got x cubed plus 3xy plus 2y cubed is equal to 17. And you want to find dy dx, right? Which means you got to take the derivative of everything. What's the derivative of x cubed? 3x squared. What's the derivative of 17? What's the derivative of 2y cubed? Is y an x? So really I have to use chain rule or implicit differentiation and say it's times dy dx. What am I going to have to use for this 3xy term here?
It's 2y cubed and not 3y squared.
Thanks, Kim. Okay, so first of all, so that should be a 6, right? Am I better now? Okay. So now what do I have to use for that 3xy term? No, wait. I want to know the principle I need to use, the rule I need to use. Product rule. So you try to do the 3xy.
Pamela tried to divorce this room.
I think she teaches this period. Okay, do you get something that looks like that? Okay, and then we can cancel out a bunch of 3's and make that a 2. And then you get all the terms that have dx, dy, dx on one side, and all the terms that don't on the other. So basically, I've got x plus 2 times dy dx is equal to negative x squared minus y. Sorry, that should be 2y squared. Or dy dx is equal to negative x squared minus y all over x plus 2y squared. Okay. All right, so it's time to clean up. Your homework for tomorrow is on the portal. It's to read 3.6. I will work on getting the homeworks together and ready for you so that maybe they'll be due on Thursday. Okay, please spray and then I guess wipe because Miss Vasily has a class coming in. Okay. Goodbye, my Zoom friends. I will see you tomorrow, some of you. Bye, guys. Was I video? Was I not? Huh. How weird. I never turned on my video. How rude.